अभी तो वीडियो बंद कर दो क्या?
हाँ बंद कर दो अभी तो
बंद किया है।
ठीक है।
अच्छा
अभी तो उन्होंने पहले दे विल स्टार्ट देयर ओन but can we see whatever that the main website shows?
मेन वेबसाइट
नहीं तो मेरा है जो उनका प्रेजेंट जो मेन वेबसाइट होगा ना जहाँ से पहले ये प्रभाकर मिलेंगे वो सब
वही लिंक पे तो ज्वाइन किया है।
अच्छा oh they are not showing anything for themselves
I don't think.
अच्छा okay yeah, let us see
Yeah.
ये हैं प्रभाकर
हाँ
Good evening, sir. Good evening, sir.
good evening
Very happy to see you, sir.
yeah I'm happy to be here right this तुम इधर बैठ जाओ तो
नहीं मैं इधर
ठीक है
मेरे को सिर्फ कैमरे का डर है, थोड़ा बैटरी 5 मिनट बंद कर सकते हैं।
हाँ 5 मिनट के लिए बंद किया वीडियो को भी फिर ऑन कर देंगे
अच्छा आपकी आवाज जा रही है।
ठीक है
आप एक बार बोल दीजिए।
हाँ maybe you leave the audio on
ऑडियो ऑन ऑडियो ऑन।
can you hear me now Prabhakar
Yes, sir. Yes, sir. We could hear
okay
you, sir.
okay great
But
yeah we'll wait till 6 o'clock no अभी तो टाइम है
yeah, but
वीडियो बंद किया।
video is off for a short while we'll just
oh,
start
okay.
when
Oh,
needed
okay, okay, okay. You off your room. Okay.
yeah maybe you should be
Right.
on in the beginning no
Yes, sir.
your picture should be on in the main screen in the beginning
Okay.
when you are talking and so on right
Yeah. Yeah, sure, sure.
okay
Ayappan, you can start to allow the participants, I think 557. Slowly, one by one, you can allow.
Yes, I'm doing it.
Ah.
रिपीट कर सकते हैं।
Joseph, can we put the flyer itself in the background? The Sunday class account.
Oh, I think that Kamal only can put like.
Ah, okay. Maybe if he has the flyer, he can.
No,
just.
you might have.
He will have it, yeah.
Yeah.
You need this as an image format. I will send it immediately.
Is the slide visible now,
Yeah,
Joseph?
yes, it is visible.
And also we are live in YouTube.
Okay.
So start, Dr. Kamal.
Yes, Joseph. Yeah, please go ahead.
Okay. A very good evening to all. I welcome all the participants and teachers, and I welcome our today's speaker, respected Professor Deepak Dhar. I welcome respected Professor H.S. Mani and other faculties from Sunday class and science enthusiast. It's very very happy to welcome you all. Today we start our beloved Professor SVM Satyanarayana's online memorial lecture series in physics. Now I invite Dr. Preeti Meher, who is also a Sunday class student. She is now working as a faculty in Central University of Thiruvarur, to explain why we start this lecture series first. Dr. Preeti Meher.
Thanks, Joseph. Am I audible?
Yes.
Thank you, sir. So, dear esteemed professors and all my dear friends, a very good evening. So we all know that early morning of 16 September marks a huge loss, a huge personal loss in lives of in each of us who have gathered here. This universe consumed Dr. SVM Satyanarayana, but the teaching and the inspiration that he left behind is going to be immortal through generations of students to come. So today is a historical day as we start Professor SVM Satyanarayana lecture series. And one of our much adored professors in India, Padma Bhushan, Professor Deepak Dhar, will be delivering this lecture. It's a great irony that Professor Satya was passionate about physics, a notch more about statistical physics, and he followed and loved Professor Deepak Dhar's work. In fact, my role here is to address why this series. All of us who learned physics from Satya knows how much Satya emphasized the strong fundamental knowledge in all aspects of physics. Through this series, we will bring the best of minds, both in India and abroad, who are engaged in teaching and research in all aspects of physics to deliver seminal lectures which will benefit the physics community. And in fact, I would like to infer to a Tirukural here, which says, Tam inburuvadu, ulagu inburak kandu, kamuruvar katrarindar. I would like to translate this in English. The learned will long for more learning when they see that while it gives pleasure to themselves, the world also derives the pleasure from it. So not only Satya lived according to this Kural, we will also continue to celebrate his life teaching, and humanity by continuing to make the knowledge dissemination our utmost priority. We will put sustained efforts to make this series reach the physics community all over the country and public at large to boost a scientific inquiry. Personally, I urge each of Satya's students who have gathered here to actively participate in this series by bringing in great speakers, organizing the event, and work on popularization and outreach to wider audience. Thank you so much for the opportunity. Please enjoy the lecture. Thank you.
Thank you, Dr. Preeti Meher. Now I invite Dr. Kamal to share Professor S.V. Satyanarayana biography as a slide.
Joseph, is my screen visible?
Yes, sir. Yes, sir. Yeah, please visible. You go ahead.
Now, is it in presentation mode?
Yes, yes, yes. Please.
Yeah, this will be a silent presentation. So I'll take 3 minutes of time.
Thank
Over to
you.
Joseph.
Yeah, thank you, Dr. Kamal. Now I invite Professor H.S. Mani to speak a few words about this talk and the event. Professor H.S. Mani. Are you able to hear Professor H.S. Mani? Okay, so I invite Dr. Ayyappan, who is also Sunday class student. Now he is doing postdoc at IMSC, Institute of Mathematical Science, Chennai, to introduce the speaker.
Good evening to everyone. I am extremely delighted to introduce Professor Deepak Dhar. The complete description of his outstanding academic career will take a lot of time. So I will give you a very brief introduction of Professor Deepak Dhar. He was born in Uttar Pradesh. He finished his undergraduation from University of Allahabad and post-graduation from IIT Kanpur. He finished his PhD at the California Institute of Technology. During his PhD, he received 2 fellowships, namely Anthony and Feynman. Later, he joined TFR as a visiting fellow, and soon after he became a faculty member. During his tenure at TFR, he made several important contributions to statistical mechanics. He also mentored 14 PhD students. He established one of the biggest and most successful statistical mechanics group in India. He also organized 5 refreshers course to train college teachers. In 2016, he retired as a distinguished professor from TAFR. Currently, Professor Deepak Dhar is a distinguished Emeritus professor at IISER Pune, and he is supported by Senior Scientist Fellowship by NASI, which was founded by Professor Meghnad Saha. For Professor Deepak Dhar academic excellence, he received numerous awards. Here I would like to mention a few. Young Scientist Award, SS Bhatnagar Award, the World Academy of Sciences S.N. Bose Medal, 3rd World Academy of Sciences Prize in Physics, J.C. Bose Fellowship, Boltzmann Medal. He is the first Indian to receive this prize. Padma Bhushan, Meghnad Saha Centenary Medal and Honorary Doctorate, both from the University of Allahabad. It is a great privilege for all of the Sunday class students to start the Professor SVM Satyanarayana Memorial Lecture Series by Professor Deepak Dhar. With this, I would like to invite Professor Deepak Dhar to deliver his inaugural lecture on entropy.
Okay. Thank you very much for a very kind introduction. I'm very happy to give my tribute to Professor Satyanarayana and start this lecture series. I actually never met him, but I read about him from the articles and stuff. And turns out that a large number of other people who have contributed to these Sunday classes are actually my teachers and friends. So Professor Mani actually taught me at Kanpur, and Kapoor and Murthy and etc. are my good friends. So I'm happy to be part of this series. So I never met Satyanarayan, but I actually met one person who kind of sounds like him. So I was in my 12th grade in Muzaffarnagar, and there was Professor Nani Gopal who used to teach us, and his home was also free for all students. Anybody could come, and there was no fees. And he would the classes will start around 8 o'clock. People just come in and drop out as they feel like, and he will keep on answering questions to everybody, and maybe brush his teeth in between, things like that. But the classes actually started from 4 o'clock till 6. In between, he went to the college when the classes were required. But he was fully devoted to teaching and didn't seem to tire. And I actually haven't met anybody else like him. But so I thought maybe Satyanarayan was like him. But in any case, let me start on this question about entropy. So this was a topic which was very favorite of Satyanarayan. And of course, you showed this formula S equal to K log omega, which is a famous formula by Boltzmann. So let me just, the origin of entropy is, of course, in the work of Carnot. And so before that, James Watt had invented the steam engine, and that brought in the Industrial Revolution. And there was a big question in the minds of people in France that somehow the steam engines in Britain were more efficient than the steam engines in France. And Carnot wanted to understand why this happens. And eventually he figured out the answer. It was not that the French scientists were less smart. It was that the ambient temperatures in France are a little bit higher than in England. And so he derived the formula for the efficiency of engines. And so if the heat sink is at a lower temperature, then you can get more entropy. So let me write that equation here. So here Q1 is the heat which comes in from the heat source, and Q2 is the heat you dump into the sink, and T1 is the temperature of the source, and T2 is the temperature of the sink. And then this quantity called delta S, if you take in heat Q1 at temperature T1, then the entropy of my heat engine increases by this amount. And now after I do a lot of stuff, I have to eventually get the engine back into the same state as I started in the next cycle. So in one cycle, you take an amount Q1 at temperature T1, then you have to dump in some amount Q2, which will be at lower temperature. So Q2 by T2 will be the change in entropy which I dump out. And this has to be bigger than what I got in because some entropy is produced. And this equation, Q1 is bigger than Q2 and the rest is used as work. And this equation gives the efficiency of the heat engine. And this quantity is delta S. And this was studied later by Carnot. And this is the sort of PV diagram. So there is a monocomponent gas. You can start with the state of the gas and then take some path to go to a different state. You will change the volume and the temperature so that it goes in this path. And then let's say this path is done very slowly, so it is quasi-reversible, quasi-static path. Then what Clausius showed was that delta Q, which depends on the path, but delta Q by T integral from A to B is independent of path. And he called it delta S, which and called it entropy. So this is the definition of entropy. You take so since it doesn't depend on path, it only depends on the endpoints A and B. One of these points can be taken to be the reference point, and then from that point you bring the system to B and calculate integral delta Q by T. That gives you the entropy. And then so this is called the thermodynamic definition of entropy. And there were two important properties of entropy. One is additivity. So if you have a big system with different temperatures and pressure and whatever all over the place, then S total can be written as integral dV of entropy density at the point V. And the second property is that in a closed system, the total change in entropy is always positive. So this is called the second law. I assume that all the students have actually seen it before, and I'm only recalling this for you. Okay, so this is the second law, and it's very important statement by Kelvin that the entropy keeps on only increases. But it's a very non-trivial definition of entropy. The point is that one doesn't have a very good feeling of what is entropy. I have a feeling for temperature. If I touch something, it is hot. Touch something else, it is cold. And okay, if that temperature is 50.1 or 50.2, I cannot tell the difference by, touching them. But then I can devise instruments like thermometers, which can detect the temperature more sensitively. And so one can say that starting from the intuitive notion of temperature, one can go to these thermometers which measure it more accurately. So the question is, can we define an entropy meter which will measure the entropy? And it turns out, unfortunately, so far nobody has managed to define an entropy meter. It is a state function, but it is not easy to find a meter which will measure entropy density or entropy of a system. So, does it seem to be easy to express the entropy in terms of the mechanical variables of the problem? So, what shall we do? Turns out that the answer was eventually found by Boltzmann, and he wrote this equation K log omega. And I will write B here because this is the Boltzmann definition of entropy. So this K is Boltzmann constant, and omega is the volume available to the phase space. And so that's a mechanical quantity because you give me a system, I have the variables of the dynamical variables Pi, Qi. And the phase space volume is in principle determined. It's a complicated object, but anyway, you take the log and that determines the entropy. So that is the definition of entropy. Okay, and a different definition was given by Gibbs. So this is Boltzmann entropy. So this I will write as Gibbs. And what he said was that suppose you start with a system in equilibrium. So it can be in various points in phase space. So the ensemble is defined by the probability distribution. What is the probability that the system will be found in a particular microstate, which I will denote by gamma. And then the Gibbs formula is minus KB integral T gamma log P gamma. Gamma is the phase space coordinate, and P gamma is the integral over them. P gamma is the probability density that you are in a small volume near gamma, and this P of P gives you the entropy as defined by Gibbs. So if you take a microcanonical ensemble, if P gamma is constant in the energy shared, and then this equation reduces to that one. If you put some constraints that the total energy, expectation value of energy is constant, then one can derive the canonical distribution and so on. These I will not do here. But there is an important difference between the Gibbs definition and Boltzmann definition. In the Gibbs definition, it is in terms of a probability distribution. So what one has some people have argued is that probability distribution is not a state function. Given as, if you give me a protocol for preparing a system, then of course correspondingly given what is the probability that the system will be found in a given configuration, that you can tell. But as such, if you give me a particular system, it is in a state, it is not in a distribution. You cannot infer the distribution from the observation of the state of the system. But I would have liked if somehow I could determine that if entropy were a state function, I should be able to determine it by taking a photograph of the system. Very precisely accurate photograph, but a photograph of the system. So anyway, that's the comment which is aside, but actually it turns out that in equilibrium, these two definitions agree for all systems of our interest, big thermodynamic systems. These two definitions will match to leading order in the size of the system, which is what we are worrying about. So we will, in equilibrium, these two definitions match and they give you the same answer. They are equivalent. But they are no longer equivalent if I go to non-equilibrium systems. If I want to extend my definition of entropy to non-equilibrium systems, then the Gibbs definition doesn't work and the Boltzmann definition continues to work. So why is that? Well, so there is this Liouville theorem, which says that if suppose you start with a system in some state, and then it has a P of gamma, and then it evolves by a Hamiltonian, then this integral will not change. Okay, so dsg by dt is equal to 0 for Hamiltonian evolution. But this sounds very bad because I can easily imagine a system like this. There is a box in which I have arranged that all the molecules, there is a partition. All the molecules are in the left, right hand side is in vacuum. But then I remove the partition. And I'm measuring the system after I remove the partition. So then these gas molecules will go to the right. Presumably the entropy of the system increases. But the system has a Hamiltonian, which is the whatever is the interacting particle Hamiltonian, and the Hamiltonian is not changing. And so Sg doesn't change in time. So Sg cannot be used as the entropy for the definition of entropy for the evolving system. So this is sort of immediate and obvious. And so after this, what shall we do? Looks like no go. So there is some longish discussion people make, which I will not do here, but you are welcome to read about it in other books. So what one can do is that if you start a system like this, then Sg will not change because the P of gamma becomes very fine grained. And if you coarse grain the stuff, then the entropy will increase. So you don't work with P of gamma, you work with coarse grained version of P of gamma. Start with P of gamma, which is the function of time. Of gamma. And then coarse grain it and then measure and then evolve and then coarse grain again and then measure. Then you will find something which can change with time. But we are not going there. And so let me get back to the main thing. So these definitions A and B are related to corresponding equations in quantum mechanics. So in quantum mechanical system, there is no phase space. But there is a Hilbert space of all possible wave functions. And the wave function can be in S Boltzmann in quantum mechanics. There is an equivalent definition of Boltzmann's definition in quantum mechanics, which is the Kb log of dimension of the Hilbert space. So for example, suppose I have a system with energy between E and E plus P, that is the microcanonical ensemble. Then how many independent eigenfunctions can be constructed, or how eigenstates of energy you can have. That will be the dimension of the Hilbert space, and the log of that gives you the quantum mechanical entropy. And this number is actually discrete. There is number is an integer, and this is well defined by the volumes. There is always some fuzziness involved, and you have to. The unit of volume in classical mechanics is not fixed, but in quantum mechanics it is known, and so this definition is sort of more comfortable for people who don't like to think about infinitesimal volumes. But anyway, there is also a definition which is equivalent of this definition with the Gibbs definition, which is called von Neumann. This is the quantum mechanical definition. And this is minus KB trace rho. Here rho is a quantum mechanical density matrix operator. And you have to take the trace of this operator, and that gives you the. It is easy to check. That is you take a microcanonical ensemble, then this will give you the corresponding answer. Okay, this is called microcanonical ensemble corresponding to QM. Okay. So, but there is also one more entropy which I want to refer to. It is not fully necessary, but maybe there is a box in which I can mention this. This is called the Shannon entropy. So Shannon entropy is defined for any random variable. If you have a random variable which takes, let's take discrete values, x1, x2, xn, with probability p1, p2, pn, then the entropy of a random variable is S is equal to minus summation pi log pi. So, for example, if I just want to toss a single coin, so, with probability half it comes up head, with probability half it comes up tail. And so, there are only just one trial with only two outcomes. But the outcome is a random variable. And I can define an entropy for this random variable, which is half log half plus half log half, that is log 2. So, there is no need to work in thermodynamics here. There is no thermodynamics involved if you just flip a single coin, right? But if you say that I will think of my pi as the probability that if I take some system, then in thermal equilibrium, then I measure its quantum mechanical state and find out what it is, then it will be with some probability you will get some answer, and that probability distribution will have this entropy. Okay, so the Shannon entropy is the sort of special case. It's a more general case, and when applied to large thermodynamical system, that becomes a von Neumann entropy. Because this pi can be replaced by this rho hat. You have to discuss a little bit about measurements and stuff, and I'm not going to go into that details here now. Okay. So, okay, but it was very interesting. What happened was that Joel Lebowitz and Goldstein and Pune and Jangi had written a paper describing these different interpretations of entropy, and they said that whatever von Neumann and James and Kinchin said in their definition of entropy doesn't actually work for non-equilibrium systems. And that was a rather striking sentence, because all these people are very highly respectable people, of course. And so I tried to understand this general idea and read their paper carefully. And I welcome you to look and read that paper. It is given My commentary on that paper is given to Prabhagar, and maybe you can, he will make it accessible to all of you. Okay, so, but philosophically, this question that does the system have an entropy? Suppose the system is in a given state, micro state, then does it have an entropy? That question is an important question. And I would say that, without getting into all kinds of complicated stuff, let us do this thought experiment. I have a beaker full of water, and it is at some temperature. And now I flip a coin. And if the coin comes up head, then I put this beaker on a heater and heat it for 5 seconds and then turn off the heater. If it comes up tail, then I don't heat it. Okay, after 5 seconds, there is a state of the system. What is it? It seems to me that it's reasonable to say that with probability half, it will be in a high entropy state because I heated it. And with probability half, it will be in a low entropy state. Okay, I think any theory we make up for the definition of entropy or whatever has to be consistent with this general expectation. But if you want to use von Neumann definition of entropy, it won't work because, after 5 seconds, there is a density matrix. Given the density matrix, there is a particular trace. So it only gives you the expected value of the entropy. It doesn't give you the possibility that with some probability half the entropy has a value S1, which is bigger than another value S2. You cannot, since entropy is just defined for the distribution, it's a single number. You cannot think of it as two possible values. So I think that's an interesting point. So Boltzmann and Leibowitz et al., they actually have a solution for this problem, and their proposal is the following. They say that we will define entropy as a state function. So what is it? So they said, let's take the phase space. I'm very bad at drawing phase space because it's in very high dimension. But, schematically, there is some phase space. There is an energy shell. There are all these states available to the system. Now, in these states, I can distinguish different types of states. Some states are kind of uniform density everywhere. Some states are more particles here than there and so on. So I will make the phase space is divided into inequivalent parts. And there is a picture which is like so very large part of the phase space consists of the states which look like the equilibrium state, but there is also some small parts which consist of states in which things are much more to the left half of the box or some such thing. Maybe this one has more particles in the middle. So the phase space can be broken into parts, each of which is macroscopically indistinguishable by some observer. And then all, you assign all the points in this region, volume gamma 1, omega 1, and here omega 2, and here omega 3, and so on. And so omega 1 is the volume of the phase space point which looks macroscopically similar to this one. And this is the value, this value is the same in all of these phase space points. And similarly for other omegas. And now you just go to a point and find out what's the omega there and take the log, that is the entropy of that state. So now it has become a state function because each omega is defined over all the phase space points. So that is their answer. There is a little bit of qualm about this, is that the definition of what constitutes equivalent is a little bit arbitrary. You cannot be, people can differ a little bit about whether I should divide it into this part or that part or that part, and how do you actually get this decomposition? Because most of the volume, 99.999 or some such thing, is in one region, which is very big, and all the rest are in very tiny bits of entropy, and tiny bits of phase space volume, and they correspond to lower entropy parts. Okay, I will not go into this further, but I think it's interesting to highlight the point that the entropy is a subtle and non-trivial concept. And I actually earlier wrote an article where I made a story about a scientist who goes to China. And in China, he works in the daytime in the office, there is no problem. He works in English, but he knows no Chinese. So in the evening, he has to go to eat in a restaurant. And since he doesn't know Chinese, the waiter brings him a menu. And he cannot read the names and stuff, but he can look at the prices. And he finds a dish which is in the correct price range, points to it, and eats it. The waiter brings in that dish. The quality of the food is good. He's satisfied and he goes home. Next day, he does the same thing. He just goes and picks one of the things in the correct range and eats it and goes. So this went on for a while. And then one day, he chose to change his restaurant. So, he was telling his colleague that, okay, I have changed my restaurant now. I like this second restaurant much more. So the person asked him that is the food better or is the food price is better or what? He said, no, the food price is the same. The quality is the same. Then why do you like the new restaurant? He said, here the menu is bigger. It has 10,000 entries, while the previous menu had only 100 entries. And I like to have more choice. Okay. Now, this story has been put up because you will say, what a silly person. What a difference does it make if the menu has 10,000 entries or 100 entries? You are only going to eat one. Right? So this person will be considered quite stupid. But it turns out that systems in which they don't have any brain whatsoever, even they do this all the time. So one should not anthropomorphize the physical system quite a lot, because for many students, they are often told that, the electron is in the excited state, it goes to the ground state because it likes to lower its energy. Now, the point is the electron has no brain and there is no sense in which it wants to lower its energy. And if everybody wanted to lower their energy, where will all the extra energy go? Okay, so it's a totally incorrect way of trying to explain that. It is true that if the electron is in the excited state, quite often you find that it goes to the lower energy state and emits a photon. But the explanation that electron wants to lower its energy is a cop-out, or it's a non-explanation, and it should not be given because it confuses the students. You could equally well say that, the electron wants to have a baby photon, and so it gives rise to a baby and then goes to the lower energy state, which is equally stupid. Okay, anyway, so coming back to my system, why does the system with no brain prefer to go into a state in which there is much more choice? So if I have a gas in a box, why does it go to a state where, the omega is much bigger? That's the question. And at this level of description, I actually don't have an answer with me. And I only say that it's an interesting question to worry about. Okay, so that is I'm not giving an explanation of the second law. I'm just saying that it is there. And it is enigmatic, it's surprising, it happens, and one can worry about why does it behave like this. Okay, but anyway, going along in the parable, so one of the explanations offered for the entropy is that, there is the system evolves and then it wants to maximize disorder. So that, what is disorder? Because if you make a measurement, you will not know which outcome will happen. So in the story, it says that the person asked, why do you want to go to this bigger restaurant? He says, my boss is very nosy. He wants to know what food I eat. And I don't want to tell him. So I go to the bigger restaurant to confuse him more. Okay? But I think it's not a very reasonable thing because the boss often doesn't care. He's not watching you all the time. It is not fair to expect that, also the gas expands whether the boss is there or not there. Right? So invoking the boss and the fact that the system will try to go into a state such that the boss becomes disordered. The disorder is in the head of the boss. It is not in the system. Okay? So that explanation doesn't work. So there is another explanation people have given. Is that, the system undergoes a, this is a variation on this argument, but let me give it in the language of this guy going in a restaurant. So now he has chosen a different way for selecting a restaurant, selecting a dish. So he goes to the restaurant, he has a dish. Next day, he remembers which dish I had got last time. And he just goes to that dish, but doesn't order the same thing again. That's too boring. He goes to the next entry with the same price. Okay, and next goes to the next entry with the same price and so on. So now the evolution is deterministic. He doesn't even have a choice anymore. The argument that the system has more, I like to have more choice, is not there. He has fixed the rule. He doesn't have any choice. But still, it evolves into a state and it still prefers to go to this bigger restaurant. The scientist, if he's behaving like an inanimate system, he will go to the state with the bigger restaurant. And why? Okay, so that is the end of my statement about this. But there are actually two more concepts of entropy which I will like to mention, but not in great detail. I think you can read about them in various places, but it's just good to have a list so that you know that these things are different. So there is another quantity which is called Kolmogorov Sinai entropy. And this is a very funny quantity. It is calling it entropy, of course, it is can be justified because these are very famous people, they gave it this name. Or they gave it they called it entropy, and then other people called it entropy as defined by Kolmogorov and Sinai. So that is the name. But if I take a box of gas, it is in equilibrium, it stays there. It's in equilibrium. So the entropy, thermodynamic entropy, goes to a constant. But the Kolmogorov-Sinai entropy keeps on increasing. It is a constant rate of production of Kolmogorov-Sinai entropy of the system. So perhaps it has nothing to do with the thermodynamic entropy. That should be clear because it keeps on, that Kolmogorov-Sinai keeps on being produced at a constant rate in a system in equilibrium, like a gas in a box. So what is this exactly? Why are they calling it entropy at all? So the answer is that you should think of this system as there is a box and there is a state of the system with all these particles are evolving and it evolves in time. So I look, this is my time coordinate and this is my all the other spatial coordinates, the phase space coordinates. Okay, so the system, or let's say not phase space coordinates, let me say all the particles are have their own trajectory, and they evolve in some way. So you don't think of the state of the system. The state of the system is at one time, that is one time slice. But I evolve it in time, so there is a succession of microstates of the system. There is a whole history. So the history is a space-time diagram, phase space times time diagram. And this diagram, if I go to bigger time, then this looks pretty chaotic. You know, the particles, the trajectories are crazy. And if you evolve it, then they don't look like this, they look different again. So you can look at the probability density of different histories and ask, what is the Shannon entropy of that distribution, and that will be some value. And if you increase the time, it will increase because it will become bigger. So that is the Kolmogorov-Sinai entropy. Okay. Last one, which is actually quite nice and useful, but it also causes a lot of confusion in the minds of students, or at least it is not very familiar. So it is called Rayleigh entropy. So Rayleigh asked this question that, okay, there is this Shannon entropy. Reference. So he said that, is this formula summation S Shannon pi log pi? Is it, can it be derived, or you just have to postulate it? So he started by saying that the entropy function for a given distribution, I would want to define an entropy function. It should have some nice behavior. So like if pi is a delta function, like there is no disorder, then the entropy should be 0. If the disorder is maximum possible, the entropy should be maximum possible. So, if all these choices are equally likely, then the entropy should be maximum. Then he said that if you have independent distributions A and B, and you have if P A B is equal to PA times PP, then entropy of AB is equal to entropy of A plus entropy of B. So from this equation, because the probability distributions multiply, it seems certainly this formula satisfies this condition. Okay, so it's there is some constant k in front, which can choose to be 1 if you like, but that is a minor matter. But he showed that actually all these conditions are satisfied by a more general distribution, by more general choice of function, and the choice of function he picked was S of q is equal to summation pi to the power q log divided by 1 minus q. So if q goes to 0, this actually P, this quantity becomes P log P. For q goes to 0, it tends to gives the Shannon answer. S range SQ tends to S Shannon. But for other values of q, it's very fine, well behaved. It will behave nicely. You can determine it by explicit formula. It is additive, so there is no problem. It is also, it is maximum when all the pi's are equal, and it gives you just log n. If there are n equally good choices, then it gives you log n. So, if I want to start with Rife and say all micro-canonical ensemble is what I like, then you get the same for all q. So it looks like, you can use this function instead of that function, and it has all the desirable properties of entropy. And so one can work with this while we have to work with this one. Turns out that it has almost all the properties of entropy, and there is one property it doesn't have, which is actually very important in applications. And that property is the equivalence of ensembles. So I can use the micro-canonical ensembles, take all the states with a particular energy, is tiny energy, and calculate the entropy. And I can take the canonical ensemble in which other states are also allowed with some low probability. And it turns out that the Boltzmann entropy in the two cases, or the Shannon entropy even in this case, will be the same in these two cases to leading order, which is what we call the entropy is the same in the canonical and micro-canonical ensemble. It turns out that this is no longer true for q not equal to 0, because the distributions are very different. And for non-zero q, the tails of that distribution matter much more than the other values, and sometimes they dominate the behavior, and f of q is very different. Okay, so Rayleigh entropy doesn't seem to be very useful in statistical physics. It has not been used. But in principle, you can take the 2D Ising model and you can calculate the Rayleigh entropy as a function of energy density in the system, or as a function of the so for in the microcanonical ensemble, it gives you the same answer, but here, if you take the canonical ensemble, then the answer will be different, and that is not very desirable. So I think that is the main reason why the Rayleigh entropies are not used. And maybe I can stop here, and if there are some questions, then I can try to answer them.
Thank you, Professor. So there are a couple of questions in the both Zoom and
Can you
YouTube.
read them out? That will be easiest for me.
Yeah, I will read it. So the first question from Devanjan Rai. So he asked, why entropy functions are concave?
Okay, I don't know concave, convex, there is a function curve. It looks concave from one side and it looks convex from the other side. But anyway, entropy functions have the property that I guess this will be the treatment James. He said that we only choose, if this property were not true, then we will not be able to get the physical behavior of macroscopic system that we expect or that we want. Suppose you define entropy in some other way, which doesn't have convexity behavior. Then you will find that you will make predictions about systems which are not seen in real life. So that is why, for example, if you take a system in which one part has density 0.5 and this has density 0.6, and there is another system where the density is 0.55, we find that system goes from here to here. Okay? And that corresponds to saying that, entropy function is a convex function. This thing has a higher entropy than that. Why is that? That's what we see. If I construct an entropy function which is not convex, it will not reproduce this behavior. It will not be useful to call it entropy.
Okay, Professor. Thank you. So there is another question.
Yeah.
Is there a book on entropy for non-scientific community?
Oh, I don't know book for entropy for non. There is a book called the strange thing we call heat, which is book by Brush. There are actually 3 books which give you the history of thoughts about heat. Okay, and it is very nice and book. It gives you a lot of history and it also has discussion of entropy inevitably. And I think that's a nice book. It depends on what you want. If you want nice stories, that's one thing. And if you want to learn about the subject in technical detail, that's a different thing. So, depending on your interest, I think, but anyway, book by Brush is very nice. There is also.
Can you write in the board, Professor, that spelling so that.
I don't remember the title exactly, the kind of motion we call heat. But you say SD brush and say under heat, and you will be able to get it on the internet. It's a very well-known book. I will give you the reference. I will send it by email.
Yeah, sure, Professor. So I will communicate to the participants.
Okay.
So there is a question from R. Rajesh.
Yes.
You mentioned that the Boltzmann entropy generalizes to non-equilibrium situation.
Yeah.
Can you illustrate how it works using the example of the expanding gas?
So this, okay, the exact calculation in many of these cases are not possible, but this particular stuff was actually studied by Dhar recently in a paper with Lebowitz together. And so I refer you to that paper and you can look at it. So they actually take this entropy and study the time evolution and then see if it, which definitions can work. Okay. Maybe I can comment about non-equilibrium. When I was writing this article about comments on the entropy paper, we got into discussion with lots of scientists who are senior scientists working in statistical physics for a long time. And they sort of said, at least some of them said, that there is no need to define entropy for non-equilibrium systems. We are happy and content with the definition of entropy only for equilibrium systems. Once you have a system in non-equilibrium, there is no clearly defined notion of temperature, there is no clearly defined notion of entropy. So one should just not talk about it. One should not talk about entropy in non-equilibrium context. And I said that I am not happy with that viewpoint or that position because Lord Kelvin said the entropy of the universe increases. And we are not referring only to equilibrium situations when we formulate the second law. If you restrict the notion of entropy to equilibrium systems, then it is much less useful and the second law will have to be reformulated as well.
Okay, Professor. There is another question from Vyasheni. Sir, could you please give me a simple definition of entropy?
So, as we said, this Boltzmann definition is good.
That S is equal to K ln omega. That's what you mean, Professor?
Yeah. Where omega is defined. I can give a very short answer, but then the corresponding symbols used or words used will have to have long explanations. That is inevitable. The short
Uh,
is not always self-explanatory, so you cannot get rid of the fact that it's a complicated concept and you just learn those 3 words, then it doesn't explain anything by itself.
Okay. So there is a question from Sivabalan. If
Hmm.
any process to attain entropy negative or when entropy attains negative?
Okay, very good. So in classical statistical mechanics, entropy is a function, but it was a log of volume, but the units of volume were not fixed. If you change the unit of volume, the entropy is defined up to an additive constant. And you can change the additive constant and you can get negative values of entropy by definition. If I choose my SA to be that entropy at 0 degree centigrade, then at -1 it will be negative. But in quantum mechanics, there is actually a, we said that it is the dimension of the Hilbert space and the dimension cannot be less than 1, it's an integer. So for quantum mechanics, this definition of entropy has to be positive. Okay? So sometimes you can work with negative entropies, but it is not necessary and it is not particularly useful. So I don't see the point of why should I try to work with negative entropies.
Okay. So there is a question from BAK, that's name.
Hmm?
He said, is the entropy increasing principle related to the Big Bang origin of the universe?
Okay. Now, so this question has been discussed a lot by people who know much more than me. But anyway, there is something called the thermodynamic arrow of time, which says that you look at the system in one state and another state, and one of them has more entropy than the other. Then the thermodynamic arrow says that this occurred before that. The arrow of time is determined by which way the entropy increases. There is another thing which is called the cosmological arrow of time, where it says that the universe started like this and eventually, let us say, it collapses again. So then the expansion of the universe tells you which direction the time is increasing. But eventually, when the universe starts contracting, maybe the time will stop, time will increase, but the entropy will start decreasing. Now, question whether if the universe starts contracting, will the entropy increase or decrease is a question which is sort of speculative, of course, but I think it is not directly experimentally relevant because, in the definition of entropy, there is this cosmological entropy which I have to add or not add, and I don't know what it is. So one can construct scenarios where it is consistent with the idea that the entropy of the gases will continue expanding, but there is an entropy generation due to dark matter, or you can introduce some new names, and one can keep on working with the cosmological arrow of time. Whether it coincides with the thermodynamic arrow of time, I don't know. If the cosmological, if the system the universe starts contracting, will the second law hold or not? I have no clue. It's a speculative question for which I would prefer not to think about.
Okay. Question from Subhashi, what are some fundamental properties of entropy which hold for both equilibrium and non-equilibrium systems?
Yeah, so I tried to list what are the fundamental problems. I don't know. I would say that for large systems, additivity is an important property, but this property does not hold when the systems become very small. They interact with each other and there is some mutual coupling and it causes chain difficulties. So there is a treatment by James. You can look up the article by James. I will also give the reference for James as well. I don't remember it offhand. But he discusses starting with some postulates about this is the behavior of entropy we like. He's able to get to this kind of a formula, Pi log Pi. And as I said, this remaining sort of generalizes that treatment and gives a more general formula which also satisfies all those principles.
So question from Debanjan Rai.
Hmm.
What about infinite dimensional quantum systems when we generalize Boltzmann entropy to quantum mechanics?
Okay, see, once you have infinite systems, then in some notion or the other, the entropy is infinite. Then you can talk of entropy density. So if the system is infinite, but you look in a local region, maybe the entropy remains finite in a local region. So that is how it is discussed usually. The infinite systems are best treated as limit of the finite.
Okay, Professor. There is a question from Anand Padmanabhan. If nature likes stability, why does entropy of the universe increases?
Okay, this question I kind of referred to. So I said that it is not good to use these anthropomorphic terms like nature likes stability. I don't know what nature likes. Perhaps this gentleman knows.
Okay.
We see some behavior. That's what happens. You are interpreting it as nature like stability. So, but I see things become more unstable, with time. So, is the Ukraine war occurring because the nature like stability? Or that is a question which one shouldn't think about when we are discussing about these questions.
Okay, Professor. So there is a question from what can you say about the entropy of vacuum?
Okay, so it's a matter of definition. So you can define the entropy of a vacuum in terms of something or the other, but if vacuum is a unique state, then its entropy should be zero because it's a pure state and it is by the formula of even the exponential, but whatever, the most sensible value of entropy would get assigned to that system should be zero. And if you, as I said, that entropy is defined up to an additive constant. So if you want 10, you can perhaps work with 10 as well. You just have to subtract 10 at some other time.
Yeah. So almost, I think, yeah. So no questions. So I have two questions from my side, Professor.
Okay, sure.
One is, so we talked about the entropy for physical systems. So what about the entropy for biological systems? Especially, we talk about evolution, human the evolution that we talk about in the science. So some school of thought is talking about so human evolution is they getting more on order. So it is, which means more order means the entropy is decreasing. Some people are arguing that the human evolution does not follow the second law of entropy, but some school of thought is saying that yes, no, still the order is the entropy is always increasing. So what can you comment about this connection between entropy or second law of thermodynamics and the biological evolution?
Yeah, so very good. So I think this question it comes up quite often, and one asks, is it true that the life can have processes which actually decrease entropy, they create more order? So that seems to be true, like one can give rise to a baby who is quite ordered structure. I mean, it's hard to think of a baby as a disordered structure, right? So where does this order come from? And the answer is there is nothing with the laws of thermodynamics which say this cannot happen. In creating an ordered substructure, you have increased the entropy somewhere else. So in order to create these ordered structures, you have to consume food which throws out a lot of entropy into the external stuff. So if you take a big system, it is quite possible that one sub-part of it becomes more ordered so long as the rest of the stuff becomes less ordered. So the entropy of the whole system increases, but the entropy of a sub-part can decrease.
Okay, Professor. So there is another question, like we have that Boltzmann definition S is equal to K ln omega.
Yeah.
So if you differentiate that S with respect to omega, that S by d omega, so we'll get almost proportional to 1 by omega, right?
I don't know what is meant by differentiate with respect to omega.
No, my question is, so how the entropy changes when I have a different value of omega. So if the rate of change of entropy with respect to omega is 1 by omega, so which means as omega increases, I mean the equilibrium system, automatically the rate is decreasing.
Yeah.
So how to understand? Mathematically is fine. Mathematically, I can understand since it's directly proportional law, so automatically the derivative is 1 by omega. But how physically we can understand when we have a large omega, the change of entropy is slowly decreasing? How to get this physical picture?
Okay, very good. So the point to realize or remember always is that omega is actually usually quite big. It is of the order of 10 to the power 100, let us say. When you change the system a little bit, it becomes 10 to the power 110. Okay, so the changes in omega are enormous. The values of omega are enormous. They are, sorry, I said 10 to the power 10 to the power 100. It's of that kind. You know, it's exponential of the Avogadro number, which is very big. Okay, so I can think of changing omega, but changing omega when the number is 10 to the power 10 to the power 20 by 1 is not experimentally accessible. You turn the knob as little as possible, and the number of states available to the system increases by a factor of 10 to the power 20 or 10. So, you know, so you can make changes in omega, but infinitesimal changes in omega are experimentally not accessible. They are always very big. So omega will be 10 to the power 20. You can make it 2 into 10 to the power 20, and you can see what is the effect of this.
Oh, I think, thank you very much, Professor. Almost, yeah, that's all the questions.
Okay.
So I think you are standing almost more than 45 minutes. Maybe you can be sit. So I request now Subhashi, who is also a Sunday class student, who is now doing a PhD in Institute of Mathematical Science. So request to propose a vote of thanks.
Okay. Switch off. But keep the audio on.
Subhashi, are you here? Can you speak? No, we could not hear you, Subhashi.
So Joseph, you can thank me. I think that is okay.
Maybe I think Subhashi's audio is having some problem.
Yeah.
I request Dr. Preeti Mehar to propose vote of thanks.
Hello.
Yeah, please, ma'am. You proceed.
Okay. So yeah, it's a great privilege to first of all, it's a very great privilege to have Padma Bhushan, Professor Deepak Dhar sir, who delivered this lecture, very insightful lecture on entropy. I'm sure, like our audience, like mostly consisting of students, they enjoyed it a lot. So thank you so much, sir, Professor Deepak Dhar sir, for enlightening us, and also about kind of discussion that we had after your lecture. And I think it's also important to acknowledge Professor Mani, who was very instrumental in getting Padma Bhushan Professor Deepak Dhar as a speaker. So thank you so much, sir, for supporting us. You have been supporting the Sunday class, though I was not a student around that time, and I hear a lot about your contribution to Sunday class. So please, sir, we want your continuous support. And I want to support all of you, like, all our past students from Sunday class who have been here. Thank you so much. In fact, a couple of them worked more to get this organized and kickstart the series. As I mentioned in my maiden speech, like, about the series, I said that, like, we had to start at some point, and I think Dr. Joseph did a wonderful job. Dr. Kamal did a wonderful job in getting Professor Deepak Dhar as a speaker for our first lecture of the series. And in fact, I also thank Dr. Ayyappan, in fact, who also was instrumental in organizing this thing. So thank you so much. I apologize if I have left someone. Thank you so much, Annalakshmi ma'am, for being here. It's a support for all of us. So hope to see you all, in fact, in more numbers, with more audience, with a great speaker in the next lecture of the series. Thank you so much. Thank you so much, sir. Thank you so much, ma'am, everyone. Thank you, friends.
Thank you all.
Thank you, Professor. Thank you all. So we will end the meeting. Thank you.
Okay. Thank you. Thank you. Right.